Over the past 5 months, a small team of engineers built an internal software application that quickly scaled to over 1 million lines of code. To hit that scale in that timeframe, they enforced a hard rule. Human developers wrote exactly 0 lines of manual code. Every single piece of this system was generated by an AI agent. That includes the core application logic, the entire suite of automated tests, the continuous integration configurations, and the background telemetry. When human developers stop writing syntax, their daily job description completely inverts. Instead of typing out functions, they design isolated environments and orchestrate the conditions that allow an autonomous agent to execute the work. This operational model is called harness engineering. But scale at this velocity carries an immediate structural risk. If you deploy high-throughput autonomous agents into a standard codebase without strict mechanical controls, the system will rapidly collapse into unmaintainable entropy. Mastering an agentic workflow requires abandoning the coding practices that work for humans. Developers have to replace them with rigid, automated scaffolding and continuous feedback loops. The first bottleneck in an agent-driven codebase is memory limit. When navigating massive, undocumented repositories, an AI's standard context window quickly becomes starved of information. The industry standard solution is to write one massive, monolithic instruction manual detailing all the repository rules. Loading thousands of lines of generalized instructions into the context window causes the agent to lose focus on the actual task and start hallucinating. If every rule is flagged as important, nothing is. The agent starts pattern matching locally, optimizing for incorrect constraints instead of navigating the broader architecture intentionally. This animated diagram illustrates the structural solution: progressive disclosure. Instead of a bloated text manual, the repository itself is organized into a structured directory tree that acts as the single, versioned system of record. The massive master file is deleted. In its place sits a strictly limited 100-line document acting purely as a table of contents. When an agent receives a prompt, it reads this short map. The map mechanically points the agent to deeper, versioned execution plans hidden within the directory, giving it only the exact context it needs. Dedicated CI jobs continuously scan the map. Developers prevent context rot and give the agent the precise focus required to scale its reasoning. Even with perfect instructions, agents face an environmental hurdle. They cannot perceive how an application actually runs. The agent is entirely blind to runtime behavior. Human developers rely on visual logs, application dashboards, and user interfaces to see what code is doing. Agents require deep agent legibility, direct mechanical access to raw output data. This diagram demonstrates the infrastructure required to build that legibility. For every single Git work tree an agent touches, the system automatically boots an isolated, ephemeral application instance alongside a dedicated observability stack. The team also wires the Chrome DevTools protocol directly into the agent's runtime, feeding it raw DOM snapshots. Because the agent perceives the front end mechanically, it independently launches the app and reproduces UI bugs. That perception extends to non-functional testing. The agent is given direct access to the application's internal telemetry and performance metrics. It queries these ephemeral logs using standard languages like LogQL and PromQL. This allows the AI to validate strict system requirements, like ensuring a service startup completes in under 800 milliseconds, entirely on its own. Equipped with this isolated environment and direct observability, a single agent can iterate on one complex task, running tests and fixing errors, for up to 6 hours completely unattended. Converting human-readable interfaces into agent-queryable data pipelines is the baseline for achieving total pull request autonomy. High-throughput autonomy introduces a major secondary risk. When a machine writes 1 million lines of code in a few months, the system is exposed to rapid architectural drift and structural decay. To prevent the codebase from deteriorating, engineers apply a strict rule: rigorously enforce the boundary invariance of the architecture, but never micromanage the specific implementations. This diagram models that solution. The entire codebase is built inside a rigid scaffold defined by explicit architectural layers: types, config, repo, service, runtime, and UI. code dependencies must strictly flow forward through these layers. Cross-cutting concerns, like authentication or telemetry, are heavily restricted. They can only enter the architecture through a single, explicitly defined interface called a provider. If an agent attempts to draw an invalid backward dependency, say making a UI component call the database repository directly, a custom linter immediately halts the process. When a linter blocks a commit, it simultaneously generates an error message that injects precise remediation instructions right back into the agent's prompt. It mechanically forces the AI to correct its structural mistake. This rigid framework also eliminates debates over subjective styling. As long as the code obeys the structural invariance, is mechanically correct, and remains legible for future agent runs, human stylistic preferences are ignored. By defining strict mechanical boundaries, developers allow the agents to operate at maximum velocity without eroding the foundational architecture. Even with perfect boundaries, autonomous generation has an inevitable byproduct. The agent occasionally replicates suboptimal code, leading to a creeping entanglement of technical debt. Initially, human developers tried to oversee and clean up this degraded code manually. Deploying engineers to clean up AI slop completely negates the speed advantage of using autonomous agents in the first place. To maintain velocity, the team adopted a radical merge philosophy. They eliminated most blocking gates and began merging short-lived pull requests immediately. In a system where an agent writes code continuously, issuing a rapid correction is cheaper than forcing a pull request to sit and wait. This animated timeline illustrates the permanent solution to that technical debt: algorithmic garbage collection. Engineers extract their structural preferences and encode these golden principles directly into the environment. Dedicated background agents then run on a continuous loop, scanning specific domains for any deviation from those principles. When they detect technical debt, they instantly issue targeted, auto-mergeable refactoring pull requests. By treating code-base hygiene as an algorithmic background process, technical debt stops being a manual chore and becomes a continuous, mechanical guarantee. This macro diagram shows the complete, self-sustaining ecosystem required for autonomous development. Progressive disclosure, ephemeral telemetry pipelines, architectural dependency linters, and algorithmic garbage collection all operate in continuous orbit around the central agent core. Observing the entire system shows where engineering discipline now resides. The effort has shifted away from writing syntax and toward the design of the environment itself. Human engineers no longer spend their days generating syntax. Instead, they focus exclusively on prioritizing the actual business goals, designing the rigid feedback loops, and calibrating the control systems that govern the AI. The defining skill of future software development is orchestrating the control systems that allow autonomous capabilities to safely scale. By delegating the rote execution of software to the machine, engineers finally decouple their output from their typing speed, allowing them to maximize their only truly scarce resource: human time and attention.